Yesterday we started with the second chapter of Jackson, which was electrostatics in vacuum, and we started from the force F1 can be written is K Q1 Q2 x1 minus x2 divided by x1 minus x2, and this is Q. What was actually our geometry? Our geometry was that if we are having a charge here which is Q2, and this charge is a distance x2 from the origin or the reference point, and we have another charge which is Q1, which is at a distance x from Q2 and at a distance x1 from Q1. So I can write from the Victorian edition that x2 plus x, x2 plus x is equal x1, and from here I can write that x is equal x1 minus x2. So it is the distance between the two charges, and if I write it in vector form, then I will have to write q here. If they are in a unit vector form, then I will have to write r squared there. Now, what was actually this k? K was equal to 1 over 4 pi epsilon naught, where epsilon naught was the permittivity of free space. So this force is F1, which is in this direction. This F1 is the force which is experienced by charge Q1 when it is in the field of Q2. And similarly, the same force is experienced by charge 2 when it is in the field of charge Q1. So I can write that F1 is equal to minus F2. This is a mutual force, and this force F1 is in opposite direction to F2, while the magnitudes are the same. So this 1 over 4 pi epsilon naught, where epsilon naught was the permittivity of free space, and this k is always equal to 1 if I use the CGS system. Now I can write this force is F1 is equal to Q1, and then E, the electric field, which is 8x1. The electric field at a point x1, and this is that point. This field is due to Q2. So this field is existing there. This field means I define another thing, which is Ex1, and from above relation, this Ex1, just don't write Q1 in it. So it is Q2 and x1 minus x2 divided by x1 minus x2 whole cube. Right? This is the electric field at a point x1, and this electric field will exist there if we put Q1 in it or not. Means the field has nothing to do with our target charge, our test charge. The field is already there, but if we put another charge there, then we will experience this F1 force. Now if I say, what about the field at any point which is x? Then x1, if I say that if I want to find out the field at any point x, then just replace x1 by x, and we will have Ex is equal k Q2, and just replace x1 by x. So x minus x2 by x minus x2 cube. This will be the electric field at any point x, at any distance x. Then we said that the field is actually due to charge Q2. Now if I get out of this Q1 and Q2 and I just write this Q is the source charge, then this will be the field of that charge, right? So for any charge, this Q2 I can write as Q. Then electric field at any distance x will be kq x minus x2 divided by x minus x2 whole cube. Now what will be x2? x2 will be actually the distance of the source, this q, from the reference point. What is x? X is the distance from the charge to any observation point. Clear? So I can write that this x, for example, if I am having many charges, then the q will go to qi, like q1, q2, q3 and so on. So I will write that the electric field at any point x will be from those source charges will be equal to k summation I runs from 1 up to n if there are n charges. Then qi, because the source charge is now q. So qi, and then x minus xi means from x I will subtract the source point distance from the reference point divided by x minus xi cube. This will be the electric field from many point charges. Now if these point charges will be clustered in a sense that they are not, you can say, separable, like continuous distribution of charges. So for continuous distribution of charges, this summation on qi, which is running from 1 up to n, will go to summation. I can write this, means this is the same form, which is n, and qi. If I divide this by a volume and multiply with a volume, then no difference will occur. So I replace the first one, which is I from 1 to n, from up to n charges, and I replace this qi by rho, and this rho is actually the volume charge distribution. I say rho of x. So this will be, and let's say this is at x prime, the location, and I will write del v. So then this one, for now, if the charges will be no more discrete, but they will be just a continuous distribution, so I can write this is, this discreteness will be covered, or let me write here instead of this a subscript xi, like the charge at one point and then the other. So then this rho will be up to rho x prime and dv. This dv I can write is d cube x prime. If I want to follow the notation, then the rho will be defined like this, such that there is a restriction on the volume that rho of x prime will be equal to limit. The volume should be infinitesimally small, because I know point is a very small thing. So this should go to 0 and then Qi divided by del V. So for continuous charge distribution, I will have this expression. So I can write E, the electric field at any point x is equal to K and d cube x prime rho x prime and x minus x prime by x minus x prime cube, where x prime will be the distance of the charge density from the reference point, and x will be the electric field at any point x from the source point, from the charge distribution. Okay, now this d cube x prime is actually the dx prime dy prime dz prime, means the volume element. So the volume element will actually be like this. Now as we have joined all the charges, and all the charges are actually now summed up, or they are integrated. So we have used the integral. There is no the continuous distribution of charges. So how we will take one point out of this distribution? For that we need a point function, and that point function is a delta function. And yesterday we discussed the delta function in more detail, but let me write few of its introductory, you can say, properties. That the delta function will be from minus infinity to plus infinity, and dx delta x minus a and f of x. So this will be equal to, like the equal do not define is f of a. And there were some properties associated 1, 2, 3, 4, 5, which we did. The Jacobian we introduced, which was the interesting situation that we derived over here. You know from the first chapter of Griffiths this thing, that this will be minus infinity to plus infinity dx delta x and f of x. Then this will be equal to f of a, f of 0. This will be f of 0. Because here the domain is actually x equal to 0, means the domain should be equal to 0. This domain equal to 0, it means x is equal to a. So here the domain will come out to be f of a. Here x is equal to 0, so f of 0, right? Now, if a situation comes in, from the Griffiths we know this thing, that if it is from minus infinity to plus infinity dx and delta kx and f of x, if this is a situation, like now x is multiplied with k, a constant, then this will be equal to 1 over k absolute and then f of a. Because you will suppose kx equal to some other function, then you will apply the derivative and it will be equal to d 1 over k absolute delta x f of x, then will give f of a, 1 over k will come in. If your situation will be that you will have this delta in a derivative form like this, that from minus infinity to plus infinity and dx delta prime x minus a f of x. then this will be equal to minus from minus infinity to plus infinity, and dx delta x minus a and f of primes of x. Means the prime from here will be shifted to this one, because this is due to the integration by parts. Similarly, we were having another result that delta x minus a. If I will reverse the domain of it like a minus x, then it will behave like an even function. The negative sign will not come out of it. And the last property in which we discussed the Jacobian relation was that from minus infinity to plus infinity, if we are having dx and delta, now the domain is another function, g of x. So if this is applied on a function, then what this thing will be equal to? So now this g of x will be equal to 0, and we will use the Jacobian relation, and this will be equal to all the zeros of g of x. So I can write this will be summation on I f of xi, where xi will be all the zeros of g of x divided by dg over dx and its value at xi's. Right? Its value at all the zeros of that g of x. We solved an example on this one as well. Then finally, from the example which we solved on this relation, we came to know that delta x squared minus a squared is equal to 1 over 2a, and delta x minus a plus delta x plus a. So this was all the review, what we did the last time. And now we will move to what will happen if we just start in 2 or 3 dimensions. In 2 or 3 dimensions, what will happen to our delta function? Like we have studied our delta function only with respect to x. What if it will be with respect to r? In r we are having x, y and z. So let's say I write the delta function is delta x minus x. One x is the capital, the first one is the small one. So I can write for 3 dimensions, I can write this will be delta x1 minus x1, delta x2 minus x2, delta x3 minus x3. And you know that the small x1, x2, x3 are corresponding to the small x1, x2, x3 are corresponding to our x, y, z variables, while the capital X1, capital X2, capital X3 are corresponding to the exact values which in our earlier case was A. So they are the some specific points. Then I can write that our delta function, which is d cube x delta x minus x f of x will become equal to f of capital X. Right? But this one is in Cartesian coordinates. What about spherical polar coordinates or cylindrical polar coordinates? Because we are having some angular dependencies there as well. You know, when it is spherical polar coordinates, we are having three variables, r, theta, and phi. R is the one which is the length variable, while theta and phi are the angular portions. In cylindrical polar coordinates, we are having r and then h and phi. So the two are the length variables and one is the angular. So how we will write our delta function and those in cylindrical polar and spherical polar. So let's start from this relation. We know that d cube x delta x, this will always be equal to 1. So I can write that if I write this d cube x in spherical polar coordinates, then this is the volume element. So I will write that from 0 to infinity, I am not including minus infinity, because our radius in spherical polar coordinates starts from 0 to infinity, while in cylindrical it will be from minus infinity to plus infinity. Then the volume element is r squared dr, and I can write from minus 1 to plus 1 a d of cos theta. Now this is a bit new for you, so I will explain this. And 0 to 2 pi and d phi. And then here is delta x.